Hi, I am Varun Joshi and welcome to day 38 of our Certified Kubernetes Administrator 2025 course. Today, we are diving into one of the most powerful parts of the Kubernetes API flow, that is admission controllers. These are gatekeepers that validate or even modify your requests before they are stored in HCD. We will explore both built-in and custom admission controllers, understand the difference between mutating and validating webhooks. So let's get started. What you see on screen is SEMA sends a command kubectl apply -f pod.yaml. This essentially will create a pod. Now, SEMA has various authentication methods to use, and we have discussed them in day 37. So, if I go here, SEMA could either be using certificates or she could be using external identity providers to log in into the cluster. And it is not just a human that will be creating resources. Even your CI/CD pipelines will be creating resources. In that case, bearer tokens will be used for authentication process. So once the request is authenticated, then we have authorization. And we also learned that there are various modes of authorization that could be used, and we also learned that RBAC is the most famous one, and it is typically that you would see in production environments. Having said that, there are also scenarios where you will see webhook authorization being used, and we also discussed that OPA is a good example which can be used as a webhook authorizer. Once the request is authorized, we learned that the request is stored. We learned that the object is created, and whatever is created we know is gets stored in HCD data store. But this is not the complete picture. There is something that sits between authorization and HCD, and that something is configured in the API server itself, like authentication or authorization. You configure that in the API server. If even if you are outsourcing the authorization part to, let's say, OPA, then also you are defining that configuration in the API server. And same for authentication. Even if you are outsourcing your authentication to external identity providers, it is still the API server that authenticates the request. The final approval comes from the API server. Similarly, that's something that sits in between authorization and HCD. It is the API server where you configure that something called admission control. Now, firstly, why do I need admission control? My life was hunky and dory. I used to authenticate, authentication succeeded, and then authorization played its role. And based on that, the resources were created. And as long as my request is both authenticated and authorized, I should be good, right? But no. The point is, when you are dealing with a production grade implementation of Kubernetes, it's not just plain authentication and authorization that you need. You also need something where you can define certain policies. For example, what if SEMA is using a public image, and in your particular implementation of Kubernetes, usage of public images is prohibited? How do you achieve that? You have no means of achieving that using authentication and authorization. And using private images is one example. But what if I want that whenever a pod is created, there should be a sidecar container automatically injected into the pod? What if I wanted certain default labels, and those labels should be available on all pods that are running in my environment? I cannot force that using authentication and authorization. Hence, we want something that sits in between authorization and HCD that will ensure that the resources that are getting created in my cluster, first, it adheres to the policies that I have set for my cluster. Second, If they are not adhering to certain standards that I have set, that request can be denied. So admission control is doing two things. First is, if the request is not in line with what I have specified, then admission control can modify that request and then forward it to etcd for storage. And it can also deny or approve the request based on the request's parameters. For example, if a request is not specifying certain labels, then deny that request. Secondly, if the request doesn't have a sidecar container, then inject that sidecar container. So hence, admission control can do both the things. It can modify and it can also validate the request, and validation involves allowing or denying a request. Now let's zoom in into admission control. We have the same diagram here. What I have done is I have expanded the admission control part. What we discussed before is admission control can both modify and validate a request. So now let's see what is happening. The first admission control is achieved using something called admission controllers, and admission controllers can be mutating or they can be validating. What are mutating admission controllers? Whenever I hear the term mutate, I get back to a movie I watched, that is X-Men, and in that movie, whoever had a modified DNA when compared to human beings, they were called mutants, and mutants had certain special powers. Some won't age, some could blow fire from their mouth, and so on. And hence they were called mutants because their DNA was modified. Hence they were called mutants. Similarly, when I talk about Kubernetes admission control, then the mutating admission controller is modifying your request. Hence, they are called mutating admission controllers. And then secondly, you have validating admission controllers. What they will do is they will see the request, and based on certain parameters or certain policies, they will either allow the request or deny the request. As simple as that. And mutating admission controllers are the ones that are applied first, and then the validating admission controllers are applied. Any doubts in this? At the very last of this lecture, we'll be doing admission controller sequence, so that the concepts of who is applied first and how it is applied, how the logic is computed, we'll see all those things at the very last of this lecture. Now, each admission controller, be it mutating or validating, they have certain plugins. So if I talk about these three that I have mentioned here, these are called mutating admission controller plugins. What you see here are called validating admission controller plugins. These are the actual plugins which are doing the legwork for you. Now let's discuss few examples of each of them so that we know how these function in Kubernetes. First is default storage class. Now I'll take you back to day 27. In day 27, there was a scenario when we had multiple storage classes and we had a PVC that specified the storage class it is supposed to use. In this example, persistent volume claim has specified that it wants to use GP3 volumes. Hence, storage class that is associated with GP3 is specified here. This part is understood, but what if this request did not specify any storage class? Then there must be some way to choose a default storage class. But if you look at the example on the left, we have GP3 and we have IO1, and none of these manifests are supplying this information. Storage class Kubernetes IO is default class true. Now let's say in our example, this was specified in GP3. If this was specified in GP3 and if there were a request that was omitting this field altogether, then by default a GP3 PV was created. And why was that? It was because I have specified that this storage class is the default storage class. And who is making that happen? If your request does not have the storage class name, that who is the one who is adding the default storage class here? It is the mutating admission controller. Hence the first one is default storage class. So this plugin, what it will do is, if you have not specified any storage class but you have also defined a default storage class, then it will automatically associate the PVC with the default storage class. Then there is default toleration seconds. This is, let's say, when you apply a taint that has an effect of no execute, that implies that whatever pods are running on that node will automatically be terminated. But for applications, a abrupt shutdown is not recommended. You should allow applications enough time to gracefully shut down. Hence you have default toleration seconds, and this timer allows, I think, 5 minutes by default for a pod to gracefully terminate. If it doesn't terminate even then only it is forcefully terminated from that node. And if you want to learn more about these things, I would recommend you watch day 22. In day 22 we discussed pod lifecycle, pod termination, and all these things in detail. So now let's go back to day 38 again. The third one is default ingress class. So we have not discussed ingress yet, but I want you to have a high level understanding. So whenever you are implementing, let's say, a Kubernetes cluster, be it on premises or in the cloud, you have options to have multiple ingress controllers. For example, if I am on, let's say, Amazon EKS, I could be using HA proxy as well. I could be using AWS's ALB, and I could also be using Nginx, for example. But when I'm creating an ingress object, but my ingress object is not specifying the load balancer that I would want to use, if my request has not specified whether I want to use ALB, HA proxy, or Nginx, then default ingress class will associate my ingress with the default ingress controller. And that default ingress controller I first must be specifying, like we did for storage class. In storage class, we said that this is the default storage class. Similarly, when you have multiple ingress controllers, you specify that this is the ingress controller that I want to be default. And once you do that, whenever you are creating any ingress resources that are not specifying ingress controllers, then the default ingress will be associated with that ingress. So what we understood from this is, why are these mutating? These are mutating because they are modifying the actual request in some way. Hence, these are called mutating admission controller plugins. Now let's discuss validating admission controller plugins. First is node restrictions. So we know that all our nodes are running kubelets. If I have, let's say, worker node 1, I would want the kubelet that is associated with worker node 1 shall only be performing actions in worker node 1 and the pods that are running in worker node 1, nowhere else. Hence, this node restriction plugin ensures that the kubelet can only modify the node on which it is running and the pods in that node. You would be asking, but Varun, why would kubelet in worker node 1 be playing with, let's say, worker node 2 or pods in worker node 2? It is not always Kubernetes. For example, let's say if your worker node gets hacked, then you do not want the hacker to have control of the kubelet and also perform actions in other nodes. So hence it is imperative that you have things in place, you have admission control in place, which will prohibit that behavior. Hence, node restriction plugin will prohibit kubelet from performing any actions in any other node but in the node in which it is running. Next is resource quota. So what happens is when you have, let's say, a production namespace, and production namespace, let's say, has been given a resource quota that this namespace cannot be using more than 50 gigabytes of memory and 24 vCPUs. If the prod namespace is already using 50 GBs and 24 vCPUs, then if there is a new request that wants some memory or some vCPU, then that request will be denied because the resource quota has been exhausted. Third one I want to discuss is namespace lifecycle. So if, let's say, a namespace does not exist, and we have seen this before, when we were creating resources and namespace didn't exist, we used to receive an error that the namespace does not exist. Hence, it is the namespace lifecycle plugin that is working under the hood and ensuring users cannot create resources in the namespaces that do not exist. And second, it also has one more important functionality. If a namespace is undergoing termination, for example, then it will disallow anyone from creating resources in the terminating namespace. That's pretty self-explanatory. Now, these plugins that we have just discussed are purely mutating, that is, they are modifying something, or they are purely validating, they are allowing or denying a request based on certain parameters. But there are also admission controller plugins that are both mutating and validating. Enlighten me, Varun. The first one is limit range. So I'll go to my GitHub notes. In day 19, we learned about limit range. And why were we using limit range? We were using limit range to ensure the pods that do not specify requests and limits, they can have certain defaults. And you can set this for CPU memory and other resources as well. So here in this YAML, we have set a default request and limit for both CPU and memory. Here are our limits and here are our requests. So whenever there is a request that does not define requests or limits, then this admission controller plugin, that is limit ranger, will add those. And we have seen this behavior in our demo. When we defined this, any requests that were not specifying requests and limits, these requests and limits that we have defined as defaults were automatically injected. We saw that. But Varun, mutation part is fine. I understand that limit range is performing that. But what about validating? What is it validating? So if I go here, we also defined a max and minimum here. We said that if a request is specifying more than 4 vCPUs or more than 8 GB bytes of memory, then that request should not be catered, because this is the maximum a pod can specify. If a pod specifies CPU and memory beyond this number, then the request is rejected. And who is the one that is rejecting that request? It is our beloved limit range validation controller plugin. Hence, limit ranger acts as both mutating and validating admission controller plugin. Then there is always pull images. So let's go to day 22. So in day 22, we learned about image pull policy, and we also learned that these policies are container level. So each container can have its own image pull policy. That part is fine. But what I want you to concentrate on, we learned certain defaults as well. So for example, if you are not specifying any tag for your image that implies you are using the latest tag, then the image pull policy defaults to always. That's understood. Second, if you are specifying a tag, then the image pull policy defaults to if not present. Now let's see why understanding this is important to understand this concept. Always pull images. What this will do is, if you have set the policy to if not present or anything else, it will roll it back to always. Hence, no matter if the image is cached or not cached, it will always pull images. Okay, that is the mutating part, Varun. If I have specified if not present, it will roll it back to always. So Varun, the first part, that is mutating, that I understand. If I have specified if not present, it will change it back to always. Or even if I have specified never, it will change it back to always. So what is the validation part? It validates credentials. Credentials for what? If you are pulling images from a private registry, then all the containers that are running should have some sort of authentication associated with them, so that they can pull the images from private registries. Now, if you do not have always as the image pull policy, then the image will be cached, and even the containers that do not have access to private registries can use that image, because if the image is locally available, then the credentials will not be used to pull the image from the private registry. Hence, this plugin helps in two things. First is it ensures that image is always pulled. Now, always pulled as in you could also have a tag or you could also have latest, but whatever you have, the image will always be pulled from the registry, be it private or be it public. And the second benefit that it gives you is it disallows containers who do not have access to that private registry or that image to use that image. Hence, you stop malicious behavior of containers where they are taking advantage of cached images. Third one is service account. So what is the mutating part? Mutating part is we have created so many containers and all the time we have not specified any service account that is to be used. But as we have understood in our last lecture where we discussed service accounts, that the default service account is automatically mounted onto our pods. And who is doing that? This is done by the mutating part of the service account plugin. But what is the validation part, Varun? Now let's say if you have deleted the default service account, then that request will error out. That implies for your custom service accounts as well. If the custom account that you have specified does not exist, then also the request will error out. Varun, everything is fine until now, but always pull images, you said that whatever I have configured for my containers, it will change that and it will default to always. But in production, I have never seen this behavior. If I write if not present, then if not present is what is used. Then how can you say this? That brings me to a very important point, and that is this one. Some enabled by default. So we have talked about many plugins, but some of them are enabled by default and some of them are disabled. And out of these, all of these are enabled by default except always pull image. Hence, you see that behavior if you have supplied if not present. If not present is the one which is used for pulling your container images. But if you want, you can enable this as well. And how do we enable this? We'll see this in the next part. Validating admission control can allow deny. So mutating admission controllers cannot deny anything. They are just modifying the requests. The denying and allowing capability is only with validating admission controllers. Now let's move to the next diagram. Admission controller. So we have good understanding of admission controllers. We also have understanding about mutating and validating admission controllers. Now that we have this understanding, I want to introduce the entire hierarchy and how it works. At the very top, we have admission controllers, and then admission controllers can be of two types. First is built-in admission controllers. These come along with your Kubernetes cluster. So when you configure your Kubernetes cluster, these are already available at your disposal. Then there are custom admission controllers. Built-in admission controllers can be classified into three: mutating, validating, and dual function. We have seen all three. Then custom admission controller, as the name implies, are custom. They are not inbuilt. They do not come by default with your Kubernetes installation. You either have an external tool do this for you, which are often called policy engines, and you might have heard of popular policy engines like OPA combined with Gatekeeper, and Kyverno is also a good choice. Then you have organization specific. Now let's say whatever requirements you have cannot be fulfilled by what is readily available in the market. Then you can write your own admission controllers. Now let's discuss what we have here. All these in white, the plugins in white, we have already discussed, so I will not jump onto those. I only want to discuss mutating admission webhook and validating admission webhook. I want you to understand one thing. If you have custom admission controllers in your cluster, then how do you call those custom admission controllers? You need some mechanism via which you can call those custom admission controllers, and that is where these come into play. So whenever the request warrants something to be checked outside, something to be checked outside of the built-in admission controllers, then it is the mutating admission webhook that calls that custom admission controller. For validation, it is the validating admission webhook that calls the custom admission controller. So these two built-in plugins, they are built in, and these built-in plugins are used to call the custom admission controller plugins. They act as a bridge to invoke custom admission controllers like OPA, Kyverno, Gatekeeper, which are implemented as webhook servers. Now, what is a webhook? In very simple terms, webhook is an HTTP callback mechanism that allows one system to notify or request another system in real time when a specific event occurs. Varun, in English, please. You have a GitHub repository, let's say. You commit something there, and as soon as you commit something, your Jenkins pipeline runs. How is that possible? That is possible because of a webhook. Whenever you commit, a webhook is triggered, and that webhook intimates Jenkins to run your CI/CD pipeline. So this is a webhook. In Kubernetes, webhooks enable the API server to invoke external services during admission requests. And what are those external services? Those external services are our custom admission controllers. So Kubernetes says, hey, external service, before I accept this request, do you want to approve, reject, or modify this request? Modify, mutation, allow or deny, validation. As simple as that. And if you have any confusions about this right now, we'll understand this in deeper details in our sequencing part. Let's move down. What is a webhook? We have seen that custom admission controllers typically run as deployment. So if you are using OPA, Gatekeeper, Kyverno, so they, or even if you have your organization specific custom admission controller, then they will essentially be running as deployments. They run inside your cluster, but in extremely rare scenarios, you could also see them running outside your cluster. Then how do I enable admission controller plugins? enable admission plugins is used to enable them. Disable admission plugins are used to disable them. Let's go to our API server and check what are enabled by default and what are disabled by default. So let's go to my terminal. I will run docker ps because I have a kind implementation of Kubernetes. I will run docker exec -it to have an integrated terminal, and the container I want to log in is this one, which is acting as my control plane node in Kubernetes. And then I want to run born again shell, which is bash. I'll press enter. Oh, I'm not in Kubernetes. I should not add double hyphens. I'll press enter, and now I am in my cluster control plane node. We know that API server runs as a static pod in kubeadm deployments. If you have any other implementation where you are running control plane as systemd service, then you will have to find these options in the unit file of your service. So I will run, let's cd into this, cd etc kubernetes, and then manifests. I'll press enter. ls, here are all my 4 control plane components whose static pod manifest can be found here. So what I will do is I'll vim into kube API server. I see enable admission plugins here, but Varun, when we were discussing here, you said that all these except always pull images are enabled by default, but I only see node restriction. Why is that? What happens is, by default in Kubernetes code itself, in API server's code itself, some plugins are enabled by default. So I would urge you to check out the documentation. The link for the documentation can be found in my GitHub notes. See that, and you will see most of the plugins that are enabled by default are in the code itself, in the API server's code itself. So hence you do not see them mentioned here. But Varun, if I want to disable any of those, how do I do that? As we saw just now, what you can do is you can add this disable flag, and then those plugins can be disabled. And I do not want you to believe me blindly. So let's do one thing. I will copy this. I will add it to my API server. I'll hit insert, and then I will add this one here. And what is that I want to disable? I want to disable service account. And if I disable this, the behavior that I should see is the service account, that is the default service account, is not auto mounted onto my containers. So let's first do one thing. Before I apply this change, I'll clear my screen in this window. I'll zoom in this a little. I will again clear my screen. I will run kubectl run my pod, and I want to use the nginx image for this one. It says the pod is created. If I run kubectl describe pods and my pod, then I will see that there is a mount, and that mount is for the service account, and that service account is mapped in this location. This part is fine, and not exactly this location will have the service account, but this location will have the namespace, token, and the certificate file. We saw that in our previous lecture. So if you have any confusions about service accounts, do watch that. So this mount is happening because the service account admission controller plugin is in action, which is mapping the default service account. And if I scroll up a little, I should also see that the default service account is mapped here. Service account is mapped, and the name of that service account is default. Now let's apply these changes, and as soon as I apply this, I just want to check the name. Is it service account or service accounts? It's just service account. I'll just save this file, and as soon as I make modifications in this, we know that the kube API server is restarted. So if I run kubectl get pods, let's run it here as well. Let's run it here itself. If I run kubectl get, I'll exit from here. and then I will run kubectl get pods. The command should take some time because the API server is restarting right now. Hence, let's allow this some time. It is saying busy. So let's me do one thing. I'll add -n kube system. Let's again run this command. My API server is in pending state right now. So let's add a -w. This will watch this and refresh this screen every 2 seconds. So now we see that the API server is in running state. Now let's create another pod. Now I will run kubectl run my pod 2 and the image I want to use is nginx. Now it says my pod 2 is created. Now I want to run a describe on my pod 2. If I press enter, you see there are no mounts here. And if I scroll up, there is no service account here. Hence, now you know for sure that there are certain plugins that are enabled by default, and you can use that disable flag if you want to disable that admission controller plugin. I hope you understand this part. Now, what I want to do is I want to revert it to its original state, the API server. So I will again exec here, and then I will vim etc Kubernetes manifest. I want to modify the kube-apiserver. I'll go here and I will completely remove this disable admission plugins. It is removed. I will press escape shift ZZ to save this. I'll exit this. Now the API server would be restarting. So let's go back to our diagrams. So we have understood how to disable or enable these plugins as per your requirement. An enable plugin was always there. You can add comma and add whatever you want to add there. Now let's see what we have next. I want to cover a certain part that we briefly covered in day 35. Day 35 we discussed authorization modes, and I want to correlate that with admission control, and I want to take an example of OPA here. So first let me explain this diagram. If you have watched day 35, this will make a lot of sense to you, and if you have not watched it, I would request you to watch that. So we have SEMA here, and SEMA is applying a pod YAML. We have the API server, which is performing the authentication part. And since it was an authorization lecture, we were zooming in into the authorization part. So whenever we talk about authorization, here authorization modes are also configured in the API server, and this is the flag. And here what we are saying is, first is node authorizer, then go to the webhook, then go to the RBAC. And we discussed this scenario based on the point that we have two requirements. First is authorizer will check whether SEMA has permissions to create the pod. And secondly, the policy only if image comes from registry.pinkcompany.com. So only allow SEMA to create the pod if the image registry from where the image is coming is registry.pinkcompany.com. And we said that this can be achieved using just a webhook, or this can be achieved with a combination of webhook and RBAC. So there was an oversight from my end in this lecture. Achieving this part is not possible by just the usage of webhook authorizer. We will require admission control here, and in this particular part I want to explain how that works so that all doubts are clarified. So let's say SEMA runs this command kubectl apply -f pod.yaml, API server authenticates, then for authorization part it checks this authorization mode flag, and then in this sequence the authorization happens. First it will come to node. Each authorizer that you specify here can either allow the request, deny the request, or it can say no opinion. Only if no opinion is given, then only the request moves to the next step. If it allows or denies, then the evaluation stops right there. It is not moved to the next one. So here node, since this is used by kubelet, it says no opinion. Then the request goes to the OPA webhook authorization. So this webhook authorizer will say no opinion. Now, OPA webhook authorization will check whether the request meets certain parameters or not, and those parameters we'll see in detail. And next it moves to RBAC. RBAC says okay, allows this request because schema is allowed to create a pod. That this part is fine, and then it moves to admission control. And we discussed in this lecture that admission control sits between authorization and HCD. So once it goes to OPA admission control, we are using OPA Gatekeeper as our custom admission controller. OPA will check whether the request is from registry.pinkcompany.com, and based on that, it will allow or deny that request. Let's say SEMA specified registry.pinkcompany.com as the place from where the image is being fetched. Then OPA will also approve this request, and then the pod object will be created. So this is the usual flow. But I want to discuss few points about OPA when it is used as a webhook authorizer. Firstly, OPA is open policy agent. You can use it in two stages of your API flow. You can use it as a webhook authorization, and we learned in day 35 that one of the authorization modes is webhook. You can use it as webhook. Secondly, you can also use as an admission controller. The diagram that you see here right now uses OPA for both authorization and for admission control. Now let's see what is happening. OPA as webhook authorizer. So these points are for this particular part of this diagram. Cannot see the whole request body, only sees user group service account, verb resource namespace, and this is what RBAC also sees. But Varun, if RBAC also sees what OPA as a webhook authorizer is seeing, then why would I use both webhook and RBAC? I can just use RBAC and get away. But there are some unique features that OPA provides when it is used as a webhook authorizer, and those features are time-based access. So for example, I will only authorize the request after 6 p.m. because I do not want to perform any changes during production hours. This is just an example. Second is network aware checks. Only these CIDRs, when the request is coming from these CIDRs, these subnets, only then I will allow that request. So these features are unique to OPA. That's why some highly secure environments may use OPA as well in the authorization part. Now next is why use OPA as webhook authorizer or any external webhook authorizer in production. Early rejection. So the request will not even reach admission control and the request will be rejected right here. That's one use case. Second is centralized access decisions. Now imagine if you are dealing with one cluster, then creating RBAC policies for one cluster is fine. But if you are running hundreds of clusters, multiple clusters, then you want to centralize all these policies. And this centralization can be provided by OPA. So what you can have is you can create a central server which takes care of all authorization. Next one is typically used in high security environments or multi-cluster deployments like we just saw. So I hope this clarifies that the requirements were two in day 35. First one was to create pods and second one was to only allow images from this registry. So the first part is permissions that can be achieved by using RBAC or OPA. You could be using OPA if you also want these features, and there are few more features. You can check the GitHub notes or online to see what are those features. and then you can also use RBAC. Understand that until and unless OPA gives no opinion, a request will not be moved to RBAC authorization. So what you could see is OPA is just checking these two things. For example, the request is coming after 6 p.m. and the request is coming from a specific CIDR which is allowed. And then RBAC could be performing the actual role-based access control based on these parameters. That's one scenario. But now what I want to discuss is until and unless this gives no opinion, it will not move to RBAC. So if OPA is fine with it, let's say if OPA says, okay, it's time-based access and it is network aware checks, all things are fine. It is after 6 p.m. and the CIDR is also allowed. Then OPA will not give allow, it will give no opinion. Only then request will move to RBAC, which will further check whether Seema is allowed to perform these actions or not, actions that are defined in the verb and the resources that are defined in her resource section. Now, I want to show you what you will see in actual production implementations. So here we do not have webhook as authorizer. We just have the defaults. Here we have node and then we have RBAC. And in the admission control, we have OPA and gatekeeper. So here is the flow that you will see in production. We have already discussed these things in detail, what is admission control and how it happens. But here I wanted to give you some example policies that you could be using. So only allow images from this registries. Containers must not run as root. All pods must have team and dev labels. Now see, so this one will be achieved via validation admission controller plugin. Containers must not run as root. This again will be covered by validating admission controller. This all pods must have team and dev label, again validating. Inject default labels if missing. This is mutating admission controller. I hope you understand this part. Now lastly, I want to discuss admission controller sequence. This is the last part of this lecture and this will connect everything together. So authentication and authorization, let's say API server is taking care of that. Then we have admission control that sits between authorization and etcd. So first Seema hits kubectl apply -f pod.yaml. API server authenticates and authorizes the request. It now reaches the mutating admission controllers. Understand that it is always mutating admission controllers that take effect first. So once mutating admission controllers have modified the request, that modified object is not yet persisted in etcd. Those changes are still in memory. Then all the validating admission controllers will verify that request, and if validating admission controller denies, then the request will be denied with an error. If validation controller allows, then the request will be allowed to be stored in etcd. Another important point that I should have mentioned initially itself, admission control only applies to write operations. So your create, modify, patch. So when you run these operations, only then admission controllers are used. And whenever you are thinking of admission controllers, think of them from etcd's perspective. If a request will be writing something to etcd or modifying something in etcd or patching something in etcd, then that request will go through admission control. But if a request is just getting the object, listing the objects, then that request will not go through admission control. Hence only requests that are write specific, that are modifying some data or creating new data, only those requests will go through admission control. Now that we understand the sequence, let's take an example. So let's say you have enabled all these and let's see how these will work. First is namespace lifecycle. We know that this is validating, so this will be skipped. Second is limit ranger. We know this is a dual function admission controller plugin. Hence, only the mutating part will be applied first, not the validating part. So mutating part will say, okay, Seema has not specified requests and limits. Let me modify her request. Then the request will go to service account. Service account admission controller plugin again has two functionalities, mutating and validating, but only the mutating part will be applied here because we know mutating admission controllers apply first, then the service account will be mapped. Let's say it was the default service account. Then we are saying mutating admission webhook. Here the request will go to our custom admission controller. Custom admission controller, let's say, wants to inject a sidecar container which is there for logging, so it will inject that container, and that container could also be for a service mesh like Istio. That is the job of mutating admission webhook. This is just mutating the request, adding new container to my request, because these admission controllers can see the full body of the request. Then I have validating admission webhook. This will also be skipped because this is a validating admission controller. Then we have resource quota. Resource quota is also validating, hence this will also be skipped. So in this entire plugins, only limit ranger, service account, and mutating admission webhook were applied, and whatever changes they did, whatever mutation they performed, all of that was stored in memory. Nothing was persisted in etcd. Now that they have run, now comes the turn of validating admission controller. Namespace lifecycle will say, okay, the namespace exists. Limit ranger, it is dual function plugin, so it will say, oh yeah, the maximums for the limit range object are adhered by SEMA, so I am fine. Then the request will go to service account. Service account will say, okay, the service account that I am about to map exists, so my validation is also fine. This will not come into picture because this was already applied. Then the validation admission webhook. This will check whether, let's say for example, the image is from a private registry. Then this will also say, okay, I am also fine. Then the request will go to the request quota. Request quota will say the quota in the namespace in which SEMA wants to create a pod is fine and her request can be moved ahead. And at this stage, both mutating and validating plugins are fine with the request, so the request is allowed and then it gets stored in etcd. If any of the validating admission controller plugins would have denied this request, then the request would have been denied. I think that's all I wanted to cover. That wraps up day 38 on admission controllers. Now you know how Kubernetes can not only authenticate and authorize requests, but also enforce custom policies before anything even touches the cluster. In day 39, we will shift gears and look at custom resource definitions or CRDs. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.